in this example, we're going to go over it. It's a static equilibrium example. All right, so it says determine the tension developed in these cables AB, AC, and AD. Now, we have three cables here, and there's a 600 Newton applied force pulling it, looks like downwards in the negative Z direction. So our goal is to find the magnitudes of tension in the three ropes. So just to give you an idea of what we're going to look for, I am just going to draw the arrows, the force arrows here. It's sort of my free body diagram. It's not the best way of doing the free body diagram. I should probably redraw it. But I think you'll understand sort of what I'm doing here. So I'm going to call this FAC. This one I'll call FAB and FAD. And our goal will be to find the magnitudes of these. So the first thing we have to do is we have to write up these three vectors, even though we don't know the magnitude, but we should break them up into I hat, J hat, and K hat. And we may have to use some position vectors here. This one kind of uses a bunch of different things. So there's obviously four forces. So I think you can see that I'm just going to call it the applied force. Maybe I'll just call this the applied force. You can call it whatever you want. You can call it F1, F2, whatever. So I'm going to write this down in terms of I hat, J hat, and K hat. So you can see here it's just going to be 0I, 0J, minus 600 K hat newtons. Now, FAC, I'm starting with that one because it seems to be the easiest. And you're probably at this point still getting used to sort of visualizing these 3D drawings. But hopefully you can see here that what you're looking at is FAC is right along the negative x-axis, pointing along that rope. So it's only in the xy plane, pointing in the negative x direction. So I'm just going to call this negative FAC I hat 0J and 0 K hat newtons. Now, FAB, this one's probably the next easiest one to look at. You can see it is only in the XY plane here, but we have to use some trig. So I think you can see that the part along the x-axis is in the positive x. This will be plus FAB sine 30 because it's along this part right here, I hat, and along the positive y direction. So this will be FAB cosine 30 J hat and 0 K hat. Now, the problem with FAD, we have to use a little bit of a technique here. So I'm just going to leave this right now. I'm going to FAD right here. Now, to find FAD, we need to use the position vectors. And this is what we did in module 1. So you can see that what I'm going to do is I'm going to find the position vector that goes from A to D. And hopefully you can see offhand that that is just going to be 1 I hat minus 2 J hat, because it's too long there. And it's going to go up 2 in the positive Z hat, so plus 2K hat meters. And of course, then the overall magnitude of that, we just take the components, square them, add them together, and take the square root. So that's going to be 1 plus 4. That's going to be the square root of 9. So it's going to be 3 meters. So that means that what we can do is I can turn that into a unit vector, 1/3 I hat minus 2/3 J hat plus 2/3 K hat. And there is no unit because it's meters divided by meters. So this just represents a direction. And what that means is we can now write FAD as the magnitude FAD times this unit vector. And so when I do that and put it up here, 1/3 FAD I hat minus 2/3 FAD J hat plus 2/3 FAD K hat. newtons. And so using all of that, that's how you are going ahead and figuring out what's actually happening here and figuring out be able to write all the vectors in terms of I hat, j hat, and the unknown magnitudes. So I'm just going to erase this now to clear up some room. I now have these four forces. Now, because it's in static equilibrium, I know that these forces have to add up to 0. So this is going to allow us to get 3 equations. So I am going to add up all the x components to be 0. 0 minus FAC plus FAB sine 30 plus 1/3 FAD equals 0. So I'm going to call that equation 1. I'm going to do something similar. So if I do this, I'm going to add up. I'm not going to even put the zeros in. I'm going to get FAB cosine 30 minus 2/3 FAD equals 0. I'll call that equation 2. And finally, let's add up all the Z components. And so this is just going to be minus 600 plus 2/3 FAD equals 0. Now at this point, we have 3 equations and 3 unknowns. So we should be able to solve. And I think you can already see that it's going to be pretty quick in terms of the algebra. So for instance, notice equation 3, we can solve easily for FAD there. This is going to give us 900 newtons. And it comes out positive, so I have the right direction on there, which I assume from tension that it was going to be pulling towards, because we're basically doing the free body diagram at A. And if I plug that into equation 2, I can now solve for FAB. And I won't go all through all the algebra. You guys know your algebra. And this is going to be 692.82 newtons. Notice I'm leaving some extra digits in the calculation there because I don't want to have any round off error when I'm using it next. And then I can take both of these and plug them into equation 1 and solve for FAC. And I get that FAC is going to be about 646.41 newtons. So these are my answers, but they're not how I'm going to put them in their final form. They all came out positive, so all my assumed directions were correct. But I want to write them to 3 digits. So my final answers, FAB becomes 693 newtons. FAC becomes 646 newtons. And FAD 900. So you'll notice I didn't round until the last step. For the simple reason is when I'm using numbers and calculations, I want to keep them as long as possible. It's only when I present the final answers that I'll do any rounding. All right. And there is basically solving a 3D static equilibrium problem. If you have any questions on this, please feel free to let me know. I'm happy to answer any questions you might have. But in the meantime, I will thank you for watching and hope that you have a great day.